John. So I've got about 10 minutes to do a quick recap on the last 5 years of remote sensing work that we've done. So I'll try and do justice to Mike Watt's 150 papers that he's got out in that time. But yeah, so basically remote sensing is the science of obtaining information about objects and areas from a distance. And to do that, we have a range of sensors and a range of platforms available to us. And the benefits of remote sensing, we can really optimize data capture. We can collect higher quality data in a more timely manner. It's less qualitative, and we can even remove people from hazardous environments. So when using remote sensing, we need to be clear of what the purpose is for the data that we're capturing. And we need to make sure that we get the right platform and the right sensor for that task. So looking at scales, if we want to cover like an estate scale or national scale, for example, we'd be using satellites, which are lower resolution, but they can cover large areas in a cost-effective manner. And at the other end of the scale, we're looking at UAVs primarily, which can do much more high definition, but tend to be more economic for smaller areas. So one of the main focuses of our remote sensing research at Scion has been LiDAR. So mainly using plane-mounted LiDAR in forestry at the moment, and a single capture can cover thousands of hectares. But at kind of outputs that we can derive from that would be sort of height, stocking, stems per hectare. For those of you who haven't seen LiDAR data before, this is what we talk about with LiDAR. It's called a point cloud. So from the point cloud, we're starting to be able to do more things than just the traditional metrics. We're doing some more stretchy things now with looking at getting DBH or taper. Also being able to get a terrain model for things like harvest planning or hydrographic modeling. So at the national or estate scale, satellites and airborne platforms come into their own. And we've published a paper recently where we're looking at the use of satellites for getting some forest metrics. So we found that we've got really good correlation, primarily with LiDAR for things like mean top height. It performs better. Basal area performs better, but satellites seem to come into their own with things like total volume, where we're getting pretty comparable results with the LiDAR. Also, satellites, in terms of economies of scale, are about 10-fold cheaper, so it's definitely something worth thinking about. At this other research that we've done with LiDAR, an early paper that we published on the GCFF program was looking at using LiDAR for stand metrics for Douglas fir. So we got some really good results. We were able to predict mean top height with an R-squared of 0.85 and DBH with an R-squared of 0.74, which is pretty good. Quite happy with that. And other research, an example would be using LiDAR to predict site index and 300 index using environmental data and satellite imagery as well. At the stand level, arguably you need greater data, greater level of resolution. So UAVs can deliver that. And at Scion, about 5 years ago, we decided to delve into the UAV space, primarily to look at the rising ideas around using UAV LiDAR. So we purchased one of the first commercially available LiDAR systems for a UAV, and the biggest craft that we could find to carry it. It was early days for the craft, and we found a few bugs with that one. And when that one fell out of the sky, we purchased another one, which is another large, relatively clunky craft, but did the job until that one fell out of the sky. And then we finally settled on the DJI range, which is being used quite commonly in forestry now, and it's really helped with the regularity of the data that we're bringing back from the field. But it did highlight the fact that our laser scanner was potentially getting a bit out of date. So recently we've purchased the Regal Minivax, which is giving us some really high quality data. point clouds coming out looking like this, where we're starting to see more of the stem as well, where there's obviously more of the value. But as well as LiDAR, we've looked at a variety of sensors from UAVs, including multispectral. So we published a paper recently where we were looking at the difference between satellite multispectral and UAV multispectral. So UAV 6 centimeter, satellite 5 meter. And we use the UAV data to calibrate satellites for looking for disease in forestry. We found that we could use satellites effectively down to an area roughly the size of 4 trees, or approximately 75 square meters. Another area that we've focused on recently is using high-quality UAV LiDAR for measuring young tree trials. And we found this to be highly accurate with an R-squared of 0.96. So it's proving to be quite a promising tool, if a little costly at the moment. And then looking at the other side of the coin, with LiDAR we're creating point clouds. So other ways of creating point clouds include photogrammetry. This image here is actually made up of a series of about 100 or 200 individual images taken from a UAV. And the way that we produce the point cloud from this, we'll plot a flight path across the area of interest with the right amount of overlap between the lines. Craft flies up and down, collects a series of overlapping images, and any point on the area of interest is seen from multiple angles from all these different photographs, so that gives us the 3D characteristics. So we can create a point cloud. To give you an idea of the cost efficiencies here, our latest laser scanner cost about $250,000. The craft, the little Phantom 4 that captured this, cost $2,500. It's not quite that simple economics. You still need a high-grade GPS and some good training to fly the craft and the software to process it, but it does work out to be a lot cheaper. So we're actively working on finding out how accurate this is at the moment as an alternative to LiDAR. So when we talk about phenotyping, we're interested in not only the forest, but also the individual trees. From our research so far, we found that using airborne scanners, we can get a really good picture of the canopy, but as we get down the tree, we start to lose the data. So something Dave Pont's going to talk about a bit more in his presentation. We've been using handheld laser scanners to really get to the nuts and bolts, the lower part of the stem in much more detail. So with these scanners, we can really start to see more about things like branching and taper. And these scanners also use something called SLAM technology. LiDAR sensors use GPS traditionally to know their location and measure the distance of objects from them. But with SLAM, it no longer needs GPS, so we can actually work in GPS-denied environments such as under canopy. Just an idea of the level of detail that we can get from these scanners. But as well as the sensors, we've also found it quite important to look into using GPS below canopy. When we're phenotyping, we need to find an individual tree within a forest stand, and trying to navigate to that with GPS that doesn't work accurately can be problematic, particularly if you're doing something like inventory. If you're trying to find these trees in the forest to calibrate your LiDAR data and you end up in this plot, there might be some discrepancies turning up. So we've tested a few different GPS that are commercially available, and we found that really having an antenna massively improves your accuracy under canopy. So moving forwards, at the moment, a large area of the New Zealand forest estate is unattainable with UAVs because of the laws around flying beyond line of sight. So this is something we're actively working with the CAA to remove these difficulties. We're looking to do more research into photogrammetric point clouds so that we can reduce the cost of capture with things like LiDAR. More data around the coverage of stems and branch characterization. And also, on that same theme, being able to access the under canopy area without having to send people in there. We're working with a few other organizations to look at flying below the canopy as well.